Hello and welcome. My name is Haibing Zhao from Karlsruhe Institute of Technology in Germany. In this presentation, I would like to propose our method to design highly bespoke, robust printed neuromorphic circuits. This is a joint work with Brojo Gopal, Michael Heffenbrock, Zhidong Yang, Michael Beigel, and Mehdi Taoui. To give you an overview of this presentation, I will discuss the basics of printed electronics, the introduction of printed neuromorphic circuits, our proposed learnable highly bespoke nonlinear circuits, the variation-aware training for printed neural networks, the corresponding experiments, and finally, the conclusion. Printed electronics refers to printing electronic devices on flexible or non-flexible substrates such as papers, plastics, or even human skins. This technology is already being used to create various functionalities including printed sensors, printed antennas, printed displays, and so on. The flexibility and low cost of printed electronics make it an excellent candidate in wearable devices, environmental, industrial, and agricultural monitoring, and so on. One of the most promising advantages of printed electronics is the high customizability due to the additive manufacturing process. We can see from this figure, compared with conventional lithograph-based subjective process, additive process requires fewer steps and equipment. Therefore, the manufacturing process can be easily adjusted to different products without much side effect or additional cost. There are multiple printing technologies providing different levels of customizability, for example, the inkjet printing, aerosol jet printing, gravure printing, and screen printing. Printed electronics also suffers from drawbacks such as printing variation. Printing variation refers to the discrepancy between actual printed values and desired values. There are multiple factors that affect the printing variation, such as the printing technologies. For example, in the inkjet printing, the variation can be influenced by the minimal printing resolution that's determined by the volume of the smallest ink droplet. Moreover, the physical properties of the functional inks and the substrates also causes printing variation. And furthermore, the printing environment sometimes also plays an important role in printing variation. In the next slides, I will introduce the preliminary of the printed neuromorphic circuits. Many researchers are exploring machine learning algorithms at hardware level. However, even to implement such a 3-input, 2-output network with 4-bit digital approach requires hundreds of transistors, which is challenging for printed electronics. Because printed electronics has generally large feature size and low integration density, and therefore it is only suitable for circuits with low device count. In this regard, analog neuromorphic circuits becomes attractive as it requires less device count, which can be seen in this table. This figure shows the schematic of a 2-input, 1-output printed neuron. In this circuit, the green part represents the resistor crossbar that performs the weighted sum operation. It can be observed that the output voltage Vz can be seen as the weighted sum of input voltages Vi, with conductance values representing the weights and bias. Following the crossbar for weighted sum operation, a 10H-like activation circuit is printed. Its characteristic curve can be described by a modified 10H function. In this function, eta is the auxiliary parameter that describes the translation and the scaling of the original 10H function. However, we should note that eta do not directly refer to the component values in the circuit, but it can be rather determined by the circuit component value omega, consisting of R1, R2, W1, L1, W2, and L2. Here, W and L are the geometric features of the transistors T in the circuit. From this figure, we can find that by changing the component values, we can obtain circuits with different 10H-like curves. Here, the legends with different colors refers to different component values. By now, with crossbar for weighted sum operation and printed 10H circuit as activation functions, we should be able to assemble more complicated networks. However, another nonlinear circuit, which is called negative weight circuit, is also necessary for a fully functional printed neuromorphic circuits. If we recall the resistor crossbar, we can find that the weights in the crossbar are represented by the conductance, which can only be positive. In this case, the negative relationship cannot be expressed. This drawback strongly limited the expressiveness of the neuromorphic circuits. To overcome this problem, we introduce the negative weight circuit, and every time a negative weight is needed, for example here, we do not print a negative conductance, but rather invert the corresponding input voltage to a negative one, like this. Note that the inversion is not a linear operation, but also a 10H-like transformation. Similarly, the eta here is the auxiliary parameter that is determined by the circuit components R1 to R5, as well as W and L. This figure shows some characteristic curves of the negative weight circuit with different component values. By interconnecting these three primitive circuits, more complicated networks can be assembled. For example, this is a 3-layer network with 3, 2, and 4 printed neurons respectively. Here, the green triangle, red circle, and blue rectangle symbolize the corresponding primitive circuits. To facilitate the design of printed neuromorphic circuits, we propose the printed neural network. A printed neural network is a machine learning model that simulates the printed neuromorphic circuits with learnable conductance in the crossbar representing the weights and bias. After training the printed neural network, the well-trained conductances will be fabricated to circuit. In the following part, I will motivate and introduce the concept of learnable nonlinear circuit. In previous work, only conductances in the crossbar, which are weights and bias, are learnable for the target task, while the nonlinear circuits are considered as predefined and fixed. In this case, the high customization provided by printed electronic is actually not fully leveraged. Therefore, in this work, we promote the bespoke design of nonlinear circuits by introducing another 2 learnable parameters. And moreover, as a side effect, the outcome of the learnable nonlinear circuit can also enable the variation-aware design of the printed neuromorphic circuits, and this part will be introduced later. To realize the learnable nonlinear circuit, there are mainly 2 challenges. First of all, to optimize the circuit component omega, we must involve it into the printed neural network. So far, we have already integrated the auxiliary parameter eta into the PNN as the activation functions and the negative weight functions. Therefore, the essential challenge is to find the transformation from physical quantities omega to eta. Moreover, since the training of printed neural networks are usually gradient-based algorithms, this transformation should also be differentiable. Therefore, we plan to use a machine learning-based model to approximate this transformation, and we refer to this transformation model as a surrogate nonlinear circuit model. The second challenge is that the physical quantities omega are not unconstrained variables. For example, we need to limit them into the feasible range to keep their characteristic curve in form of 10H. In the next slides, we will introduce the establishment of the surrogate nonlinear circuit model, and after that, we will integrate them into the PNNs with the consideration of the constraints. As we wanted to use machine learning model as the surrogate model to transform omega to eta, we need firstly to build the dataset that contains omegas and corresponding etas. For this, we first define the feasible design space and the constraints that guarantee the 10H-like shape of the characteristic curves. In this table, we can see the feasible design space of the negative weight circuit as an example. We can find that there are min-max constraints on each parameter, and moreover, there are inequality constraints in the design space. After defining the design space, we draw 10,000 points in this space with quasi-Monte Carlo sampling method, and the sampled data are denoted by omega 1 to omega 10,000. Afterwards, we employ space simulation to simulate the characteristic curves of the 10,000 sampled circuits. The green points in this figure shows the simulation result of one circuit. We then fit them by tanh function as shown by the red curve. As a result, we obtain the eta value that corresponding to the circuit component value omega. So far, we have built the dataset with input data omega and output eta. Finally, we will obtain the surrogate model as differentiable transformation from omega to eta by training model with built dataset. After obtaining the surrogate nonlinear circuit model, we are facing the second challenge, that is to guarantee the constraints on omega while integrating it to the PNNs. As mentioned before, there are mainly two constraints on omega, which is min-max constraint and inequality constraints. For the min-max constraint, we can convert it into an unconstrained optimization problem by using sigmoid function and denormalization. For example, given an unconstrained parameter w, we can pass it through a sigmoid function to keep its value in range of 0 to 1. Then, we denormalize it by omega min and omega max. In this way, the value of this part can be kept automatically in omega min and omega max. This part can then be seen as the learnable omega following min-max constraint. Regarding the inequality constraints such as R1 greater than R2, we handle the R1 with the same method as min-max constraint, but for R2, we do not directly optimize it, but rather introduce an intermediate variable, and then we pass it through the sigmoid function, and then we map it to the feasible range. For example, given an unconstrained parameter w, we can pass it through a sigmoid function to keep the value in range of 0 to 1, and then we map it to the feasible range with the help of R1. Similarly, the value of this part can be kept in R1, R2 min and R1, and this part can be seen as the learnable R2 with respect to its constraint. Let's take the negative weight circuit as an example. According to the constraints, we design the learnable parameter which are corresponding to R1, R3, R5, W, and L. Moreover, there are two intermediate parameters for the inequality constraints on R2 and R4. Then we passed the first 5 parameters through the sigmoid function and denormalized them to the feasible range. For the last 2 parameters, we passed them through the sigmoid function and mapped them to R2 and R4 respectively with the help of feasible R1 and R3. Finally, the feasible circuit component values can be transformed to the nonlinear functions in PNNs by passing through the obtained surrogate models. As a short summary, previously, only conductances in the crossbar are learnable, as shown in this chart. The learnable conductances are updated through gradient-based optimization algorithms. By now, instead of using predefined and fixed nonlinear functions, we are also able to integrate learnable nonlinear circuit into PNNs. Since each operation in this process is differentiable, the gradient can be also propagated to the learnable parameter for nonlinear circuit, meaning that the nonlinear circuits can also be updated alongside the learnable conductances. Thanks to the surrogate model, we are now able to also include the components in nonlinear circuits into the variation-aware training for PNNs. The influence of printing variation is the discrepancy of the component values which are corresponding to the weights, bias, and nonlinear functions in the PNNs. As a result, the printed neural network may generate wrong output. Therefore, it is necessary to consider the printing variation into the training of printed neural networks. Here is an intuitive example to show the variation-aware training. With variation-unaware training, the resulted parameter will be at the blue point as it yields the lowest loss value. However, due to the parameter variation, bad situations such as the red point may occur. In contrast, the result of variation-aware training might be at the green point. Although it doesn't locate at the exactly minimal point of the loss function, it is much more stable and robust against the variation of parameters. From the aspect of training objective, in variation-unaware training, the loss is formulated in this equation, where L refers to the cross-entropy loss that is corresponding to the performance of the classification tasks. G refers to the learnable conductances that are corresponding to the weights and bias. W refers to the learnable parameter for nonlinear circuits. X and Y are input and output data provided by the target dataset. Different from this, in variation-aware training, we introduce a stochastic variable epsilon to simulate the printing variation. For example, each element in epsilon can be chosen to follow a uniform distribution from 0.9 to 1.1 to reflect the plus-minus 10% printing variation. Here, the O dot symbol denotes the element-wise product. With this stochastic modeling, the training objective of variation-aware training is modified to the expected loss with respect to the printing variation epsilon. Moreover, to simplify the computation of the integration, we employ the Monte Carlo method to approximate the integration term. We then conduct extensive experiments to evaluate the proposed method and analyze the result. We tested our method on 13 benchmark datasets whose complexity matched the target application domain of printed electronics. These datasets are also used in other comparable works. We performed the proposed learnable nonlinear circuit and compared it to the fixed nonlinear circuit as a baseline. For variation-aware training, we performed 5% and 10% variation to reflect printing technologies with low and high printing variation. As a baseline, we also performed the variation-unaware training. As evaluation metrics, we calculated the expected value of the accuracy with respect to the printing variation and the standard deviation as the robustness. Finally, since the proposed method is the combination of learnable nonlinear circuit and variation-aware training, we conduct ablation study to analyze their contributions separately. In this table, we summarized the result of our experiment. By comparing the first and last row, we observed that with both learnable nonlinear circuit and variation-aware training, there is an 19% accuracy improvement and a 73% robustness improvement under 5% printing variation. And these values are 26% and 75% respectively under 10% printing variation. By comparing the second and third row with the last row, we can analyze the contribution of the learnable nonlinear circuit and variation-aware training separately. Regarding the accuracy, we can find that both learnable nonlinear circuit and variation-aware training contribute comparably to the overall improvement. However, regarding the robustness, solely using learnable nonlinear circuit even brings negative effects. In contrast, the variation-aware training provides almost all the improvement in the robustness and that can compensate the negative effect of the learnable nonlinear circuit. Let's come to the conclusion. First of all, As an emerging technology, printed electronics provides complementary advantages to traditional silicon-based technologies. But it also has disadvantages such as low device count, large feature size, and large latencies. In this regard, printed analog neuromorphic circuits become an attractive solution for printed computing systems. In this work, we focus on the bespoke design of the nonlinear circuit and the improvement of the robustness by variation-aware training. Depending on the different printing variations, the accuracy can be improved by around 20% to 25%, and the robustness can be improved by around 75%. The ablation study reveals that in our method, learnable nonlinear circuit and variation-aware training provide similar contribution regarding the accuracy improvement. Moreover, solely using learnable nonlinear circuit might slightly reduce the robustness of the printed neuromorphic circuits, but this can be totally compensated and even improved by the variation-aware training. Thank you for your attention.